Now looking at complex zeros and the fundamental theorem of algebra. So let's quickly go through these theorems or corollaries that were given. Definition, what is a complex zero? A variable in a complex number system is referred to a complex variable. A complex polynomial function f of degree n is a function of the form, this looks familiar, f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 plus a sub 1 x plus a sub 0, where a sub n minus 1 dot 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 a sub 1 and a sub 0 are complex numbers and a sub n can't be 0. N is a non-negative integer and x is a complex variable. As before, a sub n is called the leading coefficient of f, and a complex number r is called the complex zero of f if we can plug it in wherever we see an x and we get f of r equals 0. Recall, real numbers are in the subset, they're a subset of the complex number. We saw that complex numbers could be written in the form of a plus bi. And so if we had our imaginary part, d was 0, a real number is a complex number. So just remember that. Fundamental theorem of algebra. So this must be important. So it's a fundamental theorem of algebra. This says every complex polynomial of degree n, where n has to be greater than or equal to 1, has to have at least one complex zero. It actually goes further, and it says every complex polynomial of f of degree n greater than or equal to 1 can be factored into n linear factors, not necessarily distinct, because it might have more than multiplicity of 1 of the form. So we can write it as f of x equals a sub n x minus r sub 1 times x minus r sub 2 dot 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 times x minus r sub n, where a sub n, r sub 1, r sub 2, r dot dot dot, r sub n are complex numbers. That is, every complex polynomial function of degree n greater than or equal to 1 has exactly n complex zeros, some of which may repeat. So I mentioned this before, I know, last class period. So if we have a degree n polynomial, we can break it down as n linear factors. So this is what's going to really help us, is this conjugate pair theorem. So suppose f is a polynomial function whose coefficients are real numbers. So that has to have coefficients of real numbers. If we're given that, or we find that r equals a plus bi is a 0 of f, then the complex conjugate, and we denoted that with that r with a horizontal bar over it, is equal to a minus bi, has to also be a 0 of our polynomial. So corollary, a polynomial function f of odd degree with real coefficients has at least one real 0. And I think I already stated this, but I'll state it one more time. Every polynomial function with real coefficients can be uniquely factored over the real numbers into a product of linear factors and or irreducible quadratic factors. Okay, so let's start looking at some problems. Okay, so we have a polynomial in front of us, g of x, which is equal to x cubed plus 3x squared plus 24x plus 75. And we're given that negative 5i is a real 0. And from here, we want to find the remaining zeros of g of x. So there's a couple different ways that we can approach this. We can just go ahead and use our synthetic division. We know negative 5i is a 0. We could write our coefficients here. So 1, 3, 25, and 75. If we bring down 1, I have 1 times negative 5i is negative 5i. So remember, when we're adding complex numbers, we add our real parts and our imaginary parts together. So 3 minus 5i, 3 minus 5i. Let's do some work on the side. So we have negative 5i now times 3 minus 5i. So if I distribute this, negative 5i times 3 is negative 15i, and negative 5i times negative 5i, that's positive 25i squared. But recall I squared is negative 1, so this is minus 25. So we're going to put that below in the next column. So I have negative 25 minus 15i. So summing the real parts, 25 minus 25 cancels, and then we're just left with the imaginary part, negative 15i. Well, negative 5i times negative 15i. Well, negative 5 times negative 15 is positive 75, but then when we have the I squared, which is negative 1, so we have negative 75, which gives us back 0. We know we did something wrong if we didn't get back 0 here, because we were given that this is a 0 of our polynomial, so our remainder must be 0. Well, let's break it down further. We have that complex conjugate pair theorem that says if negative 5i or complex number is a 0, then the conjugate is also a 0. So positive 5i must also be a 0. This right here has degree 2. I'm not going to write it out, but I'm going to use that bottom row right here. So I have 1, 3 minus 5i, and negative 15i. So again, I know I did something wrong if I don't get 0 back for my remainder because of that conjugate pair theorem. So let's bring down my 1. 1 times 5i is 5i. Sum negative 3 minus 5i plus 5i is just 3. And 3 times 5i is 15i. So this is 0. So we can read off this last row. If this was degree 2, this is degree 1. So this right here is x plus 3. So x plus 3 is a 0 when x equals negative 3. So we have our zeros of this polynomial, g of x, are positive and negative 5i and negative 3. Let's break this down as a product of linear and or irreducible quadratic factors. And so the factor negative 5i is a 0. X plus 5i is a factor. If 5i is a 0, we know x minus 5i is a factor. Let's rewrite this because this is irreducible over the real numbers. And then let's also put in if x equals negative 3 is a 0, then we know x plus 3 is a factor. So right now we have g of x equals this. So this is a difference of 2 squares, x plus 5i times x minus 5i. So we can think of this as x squared minus 5i quantity squared. Well, 5i times 5i is 25i squared, which is negative 25. So minus a negative 25 is really plus 25. All times x plus 3. So we broke g of x down as a product of linear and irreducible quadratic factors. So the next example says, find a degree 4 polynomial with the zeros I and 1 plus I, where our polynomial has real coefficients. So let's use the fact first with I. If I is a 0, then by the conjugate pair theorem, negative I must also be a 0. That's not post. So let's look at that. We have x minus I all times x plus I. So if we distribute that out, well, this is a difference of squares. So we could just square the first term, x squared minus I squared. I squared is a -1. So minus a -1 would be +1. If we're given 1 plus I is a 0, then 1 minus I must also be a 0. So the factor is going to be, and this is where you kind of need to be careful, it's x minus this quantity, 1 minus I, and it's x minus the quantity 1 plus I. Or if it helps you to see it, just write it as, we know x equals 1 minus I is a factor. So if we get this side equal to 0, we subtract 1 and add I. So -1 plus I. So distributing my negative, that would give me the same thing, x minus 1 plus I. So x equal to 1 plus I, subtract 1, subtract I, which we would get if we distributed this -1. So x minus 1 minus I. If you multiply out factors with conjugate pair zeros or with conjugate pairs, it should come out that your coefficients are always real. So if you don't get real coefficients at the end when you simplify, then you know you did something wrong. So let's just distribute. We got x times x is x squared, x times -1 is minus x times -I is -ix. Now let's distribute the -1. So I have -1 times x is -x, -1 times -1 is +1, and -1 times -I is +I. So now distributing I times x is +ix, I times -1 is minus I, and I times -I, that's -I squared, which is the same thing as +1. So combining like terms, I only have one x squared term. So real terms, coefficients in front of x. So -x minus x is -2x. We have a ix, -ix, and a positive ix, those cancel. We have an I minus an I, those cancel. And we have 1 plus 1, which is +2. So far, we have a polynomial that has those zeros. X squared plus 1 factor, which has the zeros 1 and -I, times the factor x squared minus 2x plus 2, which has the complex zeros 1 minus I and 1 plus I. We are almost there. We just want to distribute this out, and then we have a degree 4 polynomial. So distributing our x squared times x squared is x to the 4th. X squared times -2x is -2x cubed. X squared times 2 is +2x squared. Distribute the 1. So 1 times x squared is x squared. 1 times -2x is -2x. And 1 times 2 is +2. So x to the 4th minus 2x cubed, 2x squared plus 1x squared is +3x squared, minus 2x plus 2. So we just found a degree 4 polynomial with the zeros that were given to us. So there's actually an infinite number of degree 4 polynomials with those zeros. We could multiply this f of x by any constant and get the same zeros. So they might, if you had some extra information that said, find the degree 4 polynomial with these zeros and maybe giving you another point that's on the graph, we could figure out what that A value, that constant is. Okay, so that is the last section, which is 5.7 in chapter 5.